Hi, today I will talk about the shape of the modes in planar waveguides. Let's consider a planar waveguide with a core which thickness is h. Here is x, here is z, and the electric field is along the y-axis. Here is E. Y. So it is perpendicular to the xz. From Maxwell's equations, from these two, E minus dB t, and from the second one, if we expand the curl and substitute the Fourier mode, we can calculate that beta squared minus k squared times the amplitude, this is the amplitude, not the electric field, but the amplitude of the electric field, equals second derivative electric field with respect to x. And here k squared equals omega squared my naught epsilon r. And this is k squared. Beta is a propagation constant. Now let's take a look at this equation. We have a function uy on the left hand side and a second derivative of this function on the right hand side. So which functions fulfill this condition? First of all, the exponent function, because e to the power of x and a second derivative of e to the power of x also equals e to the power of x. And sine and cosine functions, because if we take the second derivative of x of cosine x, it is cosine x, and also the second derivative of sine function is a sine function. So we have three functions that fulfill this condition. So now we have core, here is substrate, and cladding. So we can guess that in cladding and substrate the electric field decreases while we are farther from the core. We don't expect that the electric field far from the core will have a high value, so we assume that it decays in substrate and cladding. So we can guess that e to the power of x, the exponential function, is a solution in cladding and substrate. In the core, on the other hand, we can guess that it is some linear combination of cosine and sine functions. So let's make a guess that uy in a core, this is the first region, substrate is the second, cladding is the third region. In the first region is some linear combination. Let's b1, some constant, cosine chi1 x plus, let's say c1, some other constant, sine chi1 x. And this is in the core. In a second region, so it is in the substrate, we can guess that it is some a, let's say 2 times e to some gamma 2x. In this region, in substrate, x is negative, so we have gamma 2, which is positive, times x, which is negative, so it will be e to the power of some negative number, so it will decrease while we decrease the x. And in the third region, so we have a3 e to the power of gamma 3 x minus h, but this time we have to put minus here because x minus h is positive, So in order to have a decreasing electric field in the cladding, this must be negative. This chi1 equals square root of n1 squared k naught squared minus beta squared, and gamma 2 equals square root of, this time, beta squared minus n2 squared k naught squared, and gamma 3 similarly is beta squared minus, this time, n3 squared k naught squared. Here is obviously n1, n3, n2. So now we are searching for these constants b1, c1, a2, a3, and also for this beta, for the propagation constant. First of all, we must get to know these constants, and moreover we must use some characteristic equation to get the value of beta, which will be different for different modes. So in order to get these coefficients, these constants, we will use the boundary conditions. We know that this parallel EY is a parallel component of the electric field, and we know that the parallel component of the electric field is continuous across the boundary, so the electric field in the core at the boundary between the core and substrate must be the same as the electric field in the substrate at this boundary. So EY in the first region at the boundary for x, which is equal to 0, must be equal to EY in the second region for x, which is equal to 0. So let's put it down. EY in the first region for x, which is equal to 0, equals b1 cosine of 0 is just b1 plus c1 sine of 0. Sine is 0, so this is just b1. EY in the second region for x, which is equal to 0, equals a2 e to the power of 0, so this one. It means that b1 must be equal to a2. Okay. The same holds for another boundary between the core and cladding. So EY in the first region for x, which equals h, this is b1 cosine chi1 h plus c1 sine chi2 h. In the cladding, on the other hand, in the third region, where x equals h, we have a3 times e to the power of minus gamma 3 x minus h minus h. Here is 0, so this is just 1. It means that b1 cosine chi1 h plus c1 sine chi2 h equals a3. Okay. Sorry. There should be chi1 here and chi1. There is no chi2 in these equations. So we assume that the electric field at these two boundaries must be continuous. We can also assume that the first derivative of the electric field is also continuous across the boundary. So we can write that the first derivative with respect to x in the first region must be equal to the first derivative in the second region for x equals 0. EY in the first region with respect to x must be equal to the first derivative of EY in the third region for x, which is equal to h. So let's calculate these derivatives. X in the first region, we have a first derivative of cosine, which is minus sine, so we have minus b1, there will be chi1 sine chi1 x plus c1 chi1 and cosine chi1 x. First derivative in the second region will be a2 gamma 2 e to the power of gamma 2x, and the first derivative in the third region with respect to x is minus a3 times e, that will be, sorry, gamma 3 minus gamma 3 x minus h. Okay, so we have these three derivatives, and now we can use these two relations. So let's take the first one. So for x, which is equal to 0, we have sine 0, so this is 0, cosine 0, this is 1, so this is c1 chi1 must be equal to the second region for 0, this is 1, so this is a2 times gamma 2. So from this I can calculate constant c1, which is gamma 2 over chi1 times a2. So let's take the second one. So in the first region we have minus b1 chi1 sine chi1h plus c1 chi1 cosine chi1 h, and this equals e to the power of x minus h, where x is h, this is 0, so this is 1, this must be equal to minus gamma 3 a3. So now let's rewrite all these relations. We know that b1 equals a2. We know that b1 cosine chi1h plus c1 sine chi1h equals a3, and c1 equals gamma 2 over chi1 a2, and the last condition is b1 chi1 sine chi1h plus c1 chi1 cosine chi1h equals minus gamma 3 a3. Let's express everything with a2. So we can write that a2 cosine chi1h plus, and c1 is gamma 2 over chi1 times a2 sine chi 1 h, and this is A3. Okay. And this equation can be expressed as minus A2 chi 1 sine chi 1 h plus gamma 2 over chi 1 A2 cosine chi 1 h equals minus gamma 3 A3. Let's add these two equations and divide by gamma 3 the second one. So we have A2 cosine chi 1 h plus gamma 2 chi 1 A2 sine chi 1 h minus A2 chi 1 over gamma 3 sine chi 1 h plus gamma 2 over chi 1 gamma 3 A2 cosine chi 1 h, and on the right hand side we will have A3 minus A3, which means it equals 0. So we have only one equation with only one unknown A2. Okay, so now let's rearrange the terms. So we have gamma 2 over chi 1 minus chi 1 over gamma 3 times A2 sine chi 1 h, and on the right hand side we will have minus 1 plus gamma 2 over chi 1 gamma 3 times A2 cosine chi 1 h. So now let's rewrite this, and I will multiply by minus 2 both sides. So we have chi 1 over gamma 3 minus gamma 2 over chi 1 times A2 sine chi 1 h, and on the right hand side we have 1 plus gamma 2 over chi 1 gamma 3 times A2 cosine chi 1 h. So now we can derive a new characteristic equation just by dividing both sides by A2 and dividing by cosine chi 1 h. So we will have tangent chi 1 h, which equals, and here we will have chi 1 gamma 3 plus gamma 2 over chi 1 gamma 3, and here we will have gamma 3 times chi 1, and here is chi 1 squared minus gamma 2 gamma 3. So we have tangent chi 1 h equals chi 1 gamma 3 plus gamma 2 over chi 1 squared minus gamma 2 times gamma 3. So we derived a new characteristic equation, and if you take a look at this gamma and chi coefficients, these functions, they all depend, okay, 1 depends on beta, gamma 2 depends on beta, and gamma 3 depends on beta. So by solving this equation, we will get values of beta. So this is another characteristic equation, which is consistent with the previously derived characteristic equation, which I've shown you in the previous lectures. So from this equation we can get beta coefficients, but now we have to calculate also B1, A2, C1, A3 constants. There is always one unknown constant actually, because it influences the amplitude, the intensity of the electric field. So now let's write all the constants. We know that B1 equals A2. We know that A3 equals B1. It is A2 cosine chi 1 H plus C1, and C1 was gamma 2 over kappa 1 gamma 2 over chi 1 A2 sine chi 1 H, and C1 equals gamma 2 over chi 1 A2. So we have all constants actually, which depend only on A2. So now let's rewrite these three equations, substituting these constants. EY in the first region equals B1, this is A2, cosine chi 1x plus C1, and C1 is gamma 2 over chi 1 times sine chi 1 x. In the second region, in the substrate, we have A2, so this is just A2, e to the gamma 2 x. And in the third region, in the cladding, we have A3, and we know that A3 is A2 cosine chi 1 h plus gamma 2 over chi 1 A2 sine chi 1 h times e to the power of minus gamma 3 times x minus h. So we have three equations, and the only unknown is A2, but you have to assume something. You can assume that A2 is 1 for some intensity. If you have a higher intensity, then A2 will be higher. And we have to calculate beta from the characteristic equation. And knowing beta, we can draw the distribution of the electric field in planar waveguide. And how does it look like? Well, for m, which is equal to 0, this fundamental mode will look like this. And here is x, somewhere here is h, here is 0. So we have exponential decay in the third region. This is cladding, first two. This is core, and this is substrate. So in the third region, we have this exponential decay. In the second region, we also have this exponential decay is this port, and in the core we have a linear combination of cosine and sine functions, and is more or less this port. So here we have sine and cosine, so this one. Second region, this is this one, and the third region is this equation. For m, which is equal to 1, it looks slightly different. So, but once again, this first region, second, third, once again we have exponential decay in substrate, we have exponential decay in the cladding, and some linear combination of sine and cosine functions in the core. So always we have some linear combination of sine and cosine functions in the core, and exponential decays in substrate and cladding. So this electric field vanishes as we are getting further from the core. So summarizing, from Maxwell equations we obtained an equation for only one component of the electric field. On the amplitude, this Ey is the amplitude of the electric field. Then we assume that the solution of this equation must be an exponential function. So we assume that in substrate and cladding it's a good idea because the electric field cannot increase when we are getting further from the core. And we assume also that in the core it's a linear combination of cosine and sine functions. So we put down these equations and started to search for this B1, C1 and the E3 constant, and we found relations between these constants, and we could write these equations with only one unknown, A2, which influences the intensity, and from the characteristic equation we can get beta. If we have beta, then we have chi1, gamma 2 and gamma 3, because they only depend on beta. Obviously they depend also on the refractive indexes, but you know the refractive index values. If you have questions, put them in the comments below. Thanks for watching and see you next time. Bye.